Hello everybody, I'm going to be talking about ionic bonding. So, ionic bonding begins with the transfer of electrons from the electropositive to the electronegative. And you should be familiar with this little periodic table thing over here. It basically shows the electronegativity scale of the periodic table, with fluorine being the most electronegative and francium being the lowest. Basically, electropositive is the opposite of electroneg, so you can think of francium as the most electropositive. So essentially, the francium is going to want to give the fluorine an ion if they were to bind, which they really can't, but it's another story. Well, they could, but very unlikely. So, what is the ionic bond? The ionic bond is actually the Coulomb attraction. Is the Coulomb attraction. And you may be familiar with Coulomb's equation, or the Coulomb force. I will rewrite it right here really quick. It's 1. The force is equal to 1 over 4 pi epsilon naught of Q1 or times Q1 Q2 over R squared. That is messy, but it works. Now, where is the highlighter? Let's highlight it. This is a useful equation that you'll use a lot, and probably be used a lot in this book. Actually, it's used in a little bit. I'll talk about that in a little bit. Okay. So, there's two parts to this. We have to rip the electron off of one, and then the other one has to take it in. So, the first part of that is the ionization energy. The ionization energy. And that is the energy to remove the most loosely bound electron. Yeah, my writing is terrible, I know, but it's hard to write on this tablet. So this ionization energy is energy to remove the loosely bound electrons. So it'd be the energy to remove, say, an electron from sodium, which actually they have in the book here as it takes, for Na, it's 5.1 eV. So that's the energy it would basically take to rip off an electron from this sodium atom. Next off, we need the energy, or the electron affinity is what it's called. Why does the pen freak out like that? Electron affinity, and that is the energy change when the electron binds. Or basically, how does the book state it? The electron affinity doesn't really clarify it very well. Anyways, it's basically how much one of these elements pulls, and the energy that it gains with pulling in an electron. So they have an example in the book that chlorine basically pulls with 3.6 eV. So with these two, why did it highlight that green? I should have highlighted that. Let's go back. Okay, being weird. Oh wow, what is going on? I don't know what's going on. Okay. We broke it. We broke it, internet. Congratulations. Okay. Well, we'll make this green. And we will make this one blue. So we know it takes... Oh man, this tablet is tricky and kind of crappy. It takes 5.1 electron volts in order to remove the most loosely bound electron. And this thing essentially pulls, or would change, with 3.6. So it uses about 3.6 to rip off this 5.0, but that leaves, there's a difference there. And that would be 1.5. So what is this 1.5 eV? This is the net energy cost for creating a pair of electrons. So this is actually referred to as the total ionization energy. Actually, the book doesn't state it as the total ionization energy. It just says ionization energy, but that's not really correct. So I state it as the total ionization energy, because ionization energy is here. It's energy to remove the most loosely bound electron. So the total ionization energy is basically the ionization energy minus the electron affinity. So that is the energy that is basically required. This 1.5, let's write it neater. We got this. 1.5, well, whatever, is the total ionization energy. Let us... Yes, we did it, boys. Okay. So we have that there. The total ionization energy. Wow, okay. This is where it starts getting a little weirder. So the energy gain is given by the Coulomb potential. What does that mean exactly? Well, they have listed here, well, there's three parts. There's the total ionization energy, which we talked about. The lattice energy, which is the electrostatic energy gain. Energy gain by assembling lattice. And it actually doesn't really talk about what that is, which is kind of weird. But a lattice is basically a structure that is a crystalline structure of particles. So this electrostatic energy gain is actually found using this Coulomb force. It is defined as the energy gain is given by the Coulomb potential. So this is the energy gain. The lattice energy is the energy gained from the Coulomb potential. So how do we actually define that? Well, we know up here that the force is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared. Well, we want to find the energy here. Well, we can do that pretty easily. We know force is force times the displacement. It's usually written as S, but in this case we'll write it as R. Oh man, pen erase. Force times, okay, R is equal to the energy, or the work, but in this case we're going to write energy. So since we multiply this R out into the force, we're then left with 1 over 4 pi epsilon naught. And actually, this should be just the, well, that's, yeah, we'll leave it as Q1, Q2. Q1, Q2 over R. So it's a little simpler because this R's fractured out. So we know that is the energy there. So, and so we have two parts of this now. We have total ionization energy, which is the energy needed to turn the atoms into the ions and then bond them. And then the lattice energy, which is the energy gained from assembling the lattice. And so when we add those together, well, not add them together, the lattice energy which is basically the electrostatic energy gain, minus the total ionization energy, is equal to the cohesive energy, which is the total energy of this entire thing. So we kind of went in a lot of steps. First, we broke it up into the ionization energy and electron affinity. How much energy change was there? We got the total ionization energy. Then we got the lattice energy, which is the energy gain from assembling this lattice, which is basically the energy between the two, between the bonds, the electrostatic energy. And then we change those and we get the cohesive energy, which is actually a very strong energy. The book states that the cohesive energy per atom is on the order of several electron volts, which is a pretty big amount, considering, you know, how small and how, you know, seemingly small and the low charges that are involved. These are really strong forces. And so if, you know, you can work backwards. If you know the distance, you can find a lot of things. You can find the electron affinity. So they do this experimentally. They basically find things such as the radius, which would be very difficult to do mathematically because it would involve a ton of quantum mechanics that, you know, I don't think that anybody has actually figured something like that out. Maybe with a really powerful computer, because, well, beyond like a hydrogen, it's very complicated to do those type of equations. Anyways, I'm rambling on. But that's basically it. You have ripping off an electron, giving it to another. In this case, we had Na and Cl. That takes 1.5 eV. Then we have the lattice energy, which is the energy gain. And so we have the lattice energy minus the energy it took, to make the ions, and that is the total energy change. And actually, it doesn't really talk about why that's important yet, but you can kind of tell it's going to be. So thanks for watching. I know this was a confusing one. The book, uh, I think it was recommended that I get the second edition, and I probably should have, because this section in particular doesn't seem to detail things very well and has some poor wording. But if you have any questions, please hit the comments, and you can always look online. That's where I learned a lot of this stuff in the first place, and had to look up a lot of this stuff to actually clarify. So thank you.